Assalamu alaikum wa rahmatullah. Welcome back, and this is a new lecture about the network layer in the internet. So we are basically continuing our discussion on the network layer. And in the previous lectures, we talked about various topics like routing, routing tables, routing protocols like distance vector and link state, routing algorithms like Dijkstra shortest path. We also talked about quality of service and congestion control. Now we would like to focus more on the internet itself. In our internet, how does the network layer look like? Before we proceed, we have to remind you that the internet is not only one network, it's a collection of networks interconnected together. And these networks that are interconnected together to make up the internet are called autonomous systems. Autonomous means independent, so we have independent networks that are interconnected with each other. Not only independent, but these networks are of different types or using different technologies, using different standards. So this is an Ethernet that's maybe in our campus, and this is a regional internet service provider like the Etisalat network, which is in turn connected to a larger backbone. So this is something like the US backbone, and this is the Europe backbone, and both are interconnected with a line that crosses the Atlantic. On the other side, we may have some other regional internet service providers, other local area networks in companies and campuses, and so on. Okay, so the main take-home message here is that the internet is not only one network, it's many networks interconnected together. So what's the problem here? The problem is that these networks are not using the same technology. When we say they're not using the same technology, we mean that at the data link layer, the header of the data link layer is not the same. So we have an Ethernet data link layer, we have a wide area network data link layer, and so on. We could have a Wi-Fi data link layer. So we say that at layer 2, this network is not the same as this one, is not the same as this one, and so on. But the glue that allows these networks to stay connected to each other and that allows these networks to be able to communicate with each other is the fact that at layer 3, at the network layer, these different machines which are part of the different networks are all using the same protocol, which is called the Internet Protocol, the IP protocol. So the main details of the IP protocol can be understood by talking about the IP header structure. So let me remind you quickly, let's have a peek at this picture. I just want to tell you that the packet, the IP packet, has a header and it has a payload which contains the message data, in addition also to some higher layer headers such as the transport layer header. But if you focus on the network layer, we say we have a packet that has a header and also the packet has a payload. Since the beginning of the course, we have been saying that the packet header contains extra control information, which is not really part of the message. However, it's still needed to be able to deliver the packet. That extra control information basically is important to get the packet delivered. However, it's still an overhead. It's still extra. We call it overhead because it's not intended to be transmitted. Now, what kind of extra control information do we have in the packet header? This is what we would like to illustrate here. So for the next few minutes, we will focus on this picture and we will explain everything here using the picture. But if you proceed with the slides, you will find that everything is actually explained. Now, of course, you know that the packet is a sequence of bits, a sequence of ones and zeros. But to be able to illustrate the packet header using a compact area like this, we use a two-dimensional structure. So we have rows. Each row has 32 bits, in other words, 4 bytes. So this represents 4 bytes. Now, how many rows do we have in the header? 1, 2, 3, 4, 5. We have these 5 rows for sure. In addition to them, we may have some options or we may not have the options depending on the options that we need. However, any IP packet header at least has these 5 rows. So the size of the packet header is at least 5 times 4 bytes, which is equal to 20 bytes. So any IP packet header has 20 bytes in addition to 0 or more options bytes that may or may not be used. So at the end of this lecture, I'll also talk a little bit about the possible options, but we focus more on the main part of the packet header. Now, Any IP packet header begins with the first field, which is called version. We need this field simply because we have different versions of the IP protocol. Nowadays, we have IP version 4 and IP version 6, IPv4 and IPv6. In both cases, the header starts with a version field, and then depending on what we see here. So if this field says 4, it means that we will read the rest of the header in this way. If this field says 6, then we will read the rest of the header in another way that will come at the end of this chapter. Now, the next field is called internet header length. We have to specify how long the header is so that anyone who receives the packet would know when the header ends, so that what comes after the header is the payload. Why do we need this field? Simply because in case we have options, then the header may have a variable length, and depending how long the actual header is, we have to specify the length here in this field, internet header length. Now, to tell you something more, basically that internet header length specifies the length of the header, but not in bytes. So whatever you see here is the length of the header, but not in the unit of bytes, in the unit of 4-byte words. How many of these rows do we have in the header? So in case we have 5 rows, 1, 2, 3, 4, 5, it means we see the binary equivalent of 5 here. In case we have some options, we can see binary equivalents of more than 5, 6, 7, or 8, and so on. So whatever number we see here, it means that this is the header length in 4-byte words. In other words, whatever number is written here needs to be multiplied by 4 to get the actual length of the header in bytes. So if this number says 5, 5 times 4 is 20, it means that our header has 20 bytes, which implies we have no option. In case this field is equal to 6, it means that 6 times 4 is 24. So our header is 24 bytes long, and since the basic part is 20, that implies that we have 4 bytes of options, and so on. Now, the next field is called type of service. Now, type of service, if you go back to our quality of service lecture, we talked about a standard for the internet, or a proposal for the internet called diffserv, differentiated services. In differentiated services, the proposal is that packets traveling in the internet in general can belong to different classes of service. Of course, if this needs to be implemented, then in each packet we have to identify which class it belongs to, and that class goes precisely here. The next 2 bits are not used, and then now we have the total length, not of the header, but the total length of the packet itself. So this field indicates how long the packet is. Now, how long is this field itself? It is 16 bits long. So if I need to write a number using 16 bits, what is the largest number that can be represented in 16 bits? It's the case when we have 16 ones. All 16 bits are ones. And that has the equivalent of 2 to the power of 16 minus 1, which is the same as 65,535. Again, 65,535. And obviously, that would be a limitation on how long any packet is. If a packet is longer, it means that its length cannot be represented in 16 bits. So this is a limitation on the packet length. Okay, so this finishes the first row, or the first 4 bytes of the packet header. The next 4 bytes, the next row, is related to a concept called fragmentation. Now, to talk to you about fragmentation more, let me tell you that fragmentation means dividing the packet into smaller pieces called fragments, and this may happen at a router down the way. So imagine that I'm sending you a packet, and that packet begins as something large, let's say 2,000 bytes, because my local network allows for 2,000 byte packets. Now this packet will leave my network. It will go from router to router. And if a router down the road cannot handle this size anymore, or if a network down the road cannot handle this size anymore, then the router responsible, basically the router that needs to forward the packet to the next network, needs to divide the packet into smaller pieces, and these smaller pieces are called fragments. Of course, if this happens, we have to make sure that we identify, basically, we have to enter some information in the headers of each one of the fragments that allows that the final destination combines the fragment back and creates the original packet. Now, the best way to illustrate that is basically to go to the following illustrating example, a fragmentation illustration. Now, imagine that this is our packet. This is the original packet that I send you. It's not fragmented yet. That's the packet as it is. Of course, that packet has a header, and I'm just identifying some of the header values. Do you see this value identification? Any IP packet has an identification. It is something like a sequence number that distinguishes the packet from other packets. So imagine that my original packet has identification equals to X. In addition to this, we have also some other fields. This is the don't fragment field, and this is the more fragment field. Don't fragment field has a default value equal to 0. And if this field is equal to 0, it means that my packet can be fragmented on the way. So routers who receive this packet on the way are allowed to fragment the packet. If the original sender wants to avoid this for any reason, if the original sender wants to prevent its packet from being fragmented on the way, it has to start the packet with the don't fragment flag. We call it a flag because it occupies only 1 bit, so it can be 0 or 1, as if we're raising the flag or putting the flag down. So if I make this flag equal to 1, it means the packet is not allowed to be fragmented. So let me go to that original packet that I sent to you. It has don't fragment equals to 0, which is the default value. It means that it can be fragmented down the road. Now, the second flag is called more fragments. And in case the packet does not have any fragments that belongs to the same packet, it has to be equal to 0. So more fragments is equal to 0, which means that this packet is whole and there are no other fragments that belong to the same packets are on the way. So obviously, these are default. This is a default value for a packet that has not been fragmented yet. Since the packet has not been fragmented yet, it means that we don't have any fragments that belong to the same packet. That's obvious. Okay, so these are the values of the header field that we're interested in. Now imagine that I send you this packet, it travels down the road, it goes on its path, and then a router later on wants to divide this packet into smaller fragments because the network it's connected to cannot handle this size anymore. So in this example, the router divides the packet into 4 pieces, and each piece is called a fragment. So this is fragment 1, fragment 2, and fragment 3. If we take these payloads and combine them together, it makes the actual original payload. However, since from the time of the fragmentation, each fragment will be traveling on its own, and they will only combine at the final destination, each fragment needs to have a complete header. So the original header needs to be copied in each fragment, because from now on, each one of these fragments will be traveling through the network on its own. But we have to be careful on the actual values that we have in the header. So at the time of fragmentation, when a router decides to fragment or divide this packet, we have to be careful with the header values. Now, let me start with identification. This identification field identifies which original packet the fragment belongs to. So going back here, since the original packet has identification equals to X, it means each one of the 3 fragments needs also to have identification equals to X, ID equals to X, identification equals to X. So these values are all the same. So if someone receives the 3 fragments, they would know these fragments belong together. They have the same identification. I have to combine them to make up the original packet. Now, how do I know the order? So if I receive the fragments, I know they belong together. They must be combined. How do I know? How does the final destination know that this is the first fragment and this is the second and this is the third? That comes from the fragment offset field. So the fragment offset field basically carries the relative position of the fragment in the context of the original packet. So the offset field would tell that this fragment comes at the beginning, this fragment comes at this position, and this fragment comes at this position. So once we combine them, we have them in the correct order. Okay, now focus on the more fragment flag. Do you remember the more fragment flag? It is used as follows. Since this is the first fragment, it means that we still have more fragments that belong to the original packet, and that's why we have mf equals to 1. So the first fragment has mf equals to 1. The second fragment also have mf equals to 1 because it's still not the last fragment. So this just says that we still have a fragment to come. Only in the last fragment we have mf equals to 0, which is like a double check. So anyone receiving all the fragments by seeing mf equal to 0, it means this is the last fragment, I have everything. Okay, so that's the deal with the second line or with the second row related to fragmentation. Again, to recap, fragmentation means a router down the way divides the large packet into smaller fragments because it cannot deal with this size anymore, or in case it cannot deal with this size anymore. To make sure that the final destination can recombine the fragment back into the original packet, we have to include some information like identification. So the identification field has to be indicated in each fragment, and this needs to be the same as the identification of the original packet. In addition to this, we have a fragment offset, which identifies the relative position of each fragment in the context of the original packet. Okay, so this finishes the second row, and we can go to the third row. We start with time to live. So that time to live field occupies 8 bits. So if you see 8 bits, so what is the use of this time to live? It is exactly the same as the age field that we talked about in the context of link state routing. So that time to live identifies how long the packet is allowed to live in the network, to stay in the network. And in practice, it is being used as the maximum number of hops the packet is allowed to be forwarded. How is this used exactly? The original sender starts with a large value, and to use the largest value, obviously we have 8 bits. 2 to the power of 8 minus 1 is 255. That's the largest number that we can put here. So if we use that and we send the packet, it means it goes to the next router. Before the next router forwards, this is decremented by 1, it becomes 254. And then the next router will have to decrement by 1, and so on. Now, if this packet arrives at the destination before the time to live hits 0, we are okay. But if for any reason this packet does not arrive at the destination, maybe because of some mistakes or errors, in that case we have the time to live as a precaution. So when this field hits 0 and the packet is still in the network, the router that sees it would just drop the packet. The next field is called protocol, and this field basically carries information about the next protocol used. We are talking about the network layer here. Now, when the network layer at the destination host finishes examining and dealing with the packet header, basically the packet header needs to be removed, and then we have the actual transport layer unit. Now, layer 3 needs to know what is the transport layer protocol it needs to give the packet to. What is the higher layer protocol it needs to hand the packet to? For example, is it TCP or UDP? So at the transport layer or at layer 4, which is the layer coming after network layer, we could have several protocols working, and we need to know which is the protocol that we have to give the packet to. That's why every packet carries here in this field, it carries what is the next layer protocol that will handle the actual data unit. Now, the next field is called header checksum, and it's used for error detection. Now, it's a very simple error detection mechanism that can be used to check any errors in the packet header itself. Now, since we know that the packet header is like a sequence of binary data, before I send you the sequence of binary data, I add this data up, I find the sum, and I put the sum here, and when you receive the header, you will do the sum yourself and compare against what you see here. So imagine, as an analogy, I want to send you 3 numbers, 5, 6, and 10. Instead of just sending you the 3 numbers, I send you the three numbers, 5, 6, and 10, and I also send you the sum. So what is 5 plus 6 plus 10? It's 21. So I send you the three numbers, and I tell you the sum is 21. So if you receive the three numbers, you just add up yourself and you compare. Do you have the same sum? Then you will assume that you don't have errors. If you have a different sum, then maybe we have an error in some of the numbers. So basically, you can ask for retransmission or something of that sort. Okay, so we go to the next field, which occupies the whole 32 bits. Again, 32 bits is equivalent to 4 bytes, and this is the source IP address. So in this field, we have to indicate what is the IP address of the source, and we also indicate what is the IP address of the destination. In the last lecture, before we went for our distance learning period, we talked about the details of the IP address in full. So to recap, every machine has an IP address, which basically reflects what is the network you are connected to and which host are you on the network. And in total, this is in 32 bits, and we have to specify the source and the destination that the packet is going to. Okay, so in addition to this, we may have some options in case some special options are needed for sending the packets. And let's move on. So this is the explanation of everything we said. And now let me point to some of the options that might be used in transmitting packets. First of all, we might need some security. If some security mechanisms are used, then maybe we have to add some more information related to the security mechanism, and this goes to the option of the packet. In case we're not using security mechanism, then this option is not needed. So I don't want to be exhaustive. This is datasheet kind of information, but let me give you one more example. Strict source routing. Now, the normal way packets get routed in the internet is that the routers themselves decide how to forward the packets. So if my packet goes to the next router, that router will check what is the destination address, and then it will use its own routing table to decide where it will send the packet next. Now, in some cases, the source itself, so that's why we call it source routing, the source itself, for some reasons, including security itself, for some reasons, the source wants to decide on the full route on its own. So I don't want to leave deciding which way the packet will go. I don't want to leave that to the routers. I want to decide on my own. So in that case, I have to specify the full path in the options. So the options would just carry what is the path that my packet goes through. And if that option is used, routing becomes very easy to the router. So when my packet goes to the next router, it will just check from the options what is the next device, and then it will forward and so on until the packet arrives at the destination. So as you just noticed, in some cases, we might need some extra options that need basically extra information to be put in the header. And for that, we have the options field. So this basically, and we talked about the IP address already. So this finishes this lecture, and I wish you all the best until I meet you again.